Welcome to Hopkins at Home. Hello, everyone. So to begin with, I've done my homework, and hopefully it'll go well, which was to show you the polarization experiment. So I'll get to that right now. So I'll start by turning on the laser. I set up a laser over by here. And let's see if, oops, wrong way. So you should see a bright spot right here. I will dim another light so it's even more apparent. Can you see it? I'll actually use polarizers. So you still see the spot? And I'm going to rotate one polarizer versus the other. It should be dimming. Now it goes away. There it is. There it goes away. I know that's not super exciting, but from the context, the basic idea was that there's this polarization with light, which is associated with an angular momentum. And that angular momentum of light can be passed to particles. And that's actually very relevant for today's topic of magnetic sensing. So, without further ado, so first we'll briefly discuss what magnetic fields are. I'll give a brief overview then of some what we would call classical magnetometers, even though they involve quantum mechanical effects. Magnetic phenomena we're interested in measuring and why you need something like a quantum magnetometer. And then I'll discuss three different quantum magnetometers. A superconducting interference device. There's that nice article by John Clark. If you haven't had a chance to read it, I'd recommend reading it. I think it's really well written. Very approachable and very thoughtful. Atomic vapor magnetometers. And then something that's new on the horizon, and actually what my work's involved with, is developing solid-state artificial atom magnetometers. So this is a slide I'll keep bringing up throughout the lectures. What do we mean by quantum sensing? The most basic level, we're looking at energy states that are quantized, and we utilize that quantization to perform the measurement. More deeply, we use the coherence of these quantum mechanical states to perform the measurement. And then something that's still a stretch goal is utilizing entanglement, which we're saving to the last lecture to discuss, to improve the measurement. And the magnetometers we'll be discussing today are atomic vapors. And then this is a diamond nitrogen vacancy-based magnetometer. At the end, I'll send you the link in the chat to the Wired article this came from, or via email. So to magnetic fields. If you have a wire carrying a current, called a current I, there will be a circulating magnetic field going around that wire. And if you look in the direction R, so we're assuming like this infinitely long wire, so we don't have to worry about finite size effects. And as you go out, the magnitude of that field drops inversely with the distance from that wire. And that wire is going in a circular direction. So if we were to talk about it as a vector, so a vector has a magnitude and direction, then it would be going that way in an angular way. Now, if you take a wire and you make a big loop, which we call a solenoid, You can generate a magnetic field inside that solenoid and outside that outside that solenoid by running a current through it. But conversely, if you have a changing magnetic field, so say like an alternating current magnetic field, it'll induce a voltage. That's from Faraday's law that you can measure with such a coil. So there's a certain symmetry there between electric and magnetic fields, which actually goes very deep. But given time constraints, we won't discuss. What too far? So here's the first magnetometer. This magnetometer, it's low power. It has a fairly high bandwidth. You can measure signals up to 500 kilohertz. So it has femtotesla sensitivity, that's 10 to the minus 15. It's very sensitive. And that is essentially a solenoid that you then have an amplifier and you measure that induced electric field from the magnetic field that goes through the coil. So that's very basic. That's obviously not a quantum magnetometer, but that's very impressive, right? So now you see kind of the competition. This also is not a quantum magnetometer, although it relies on a quantum mechanical effect. So this is the highest end of a magnetoresistive magnetometer. And there's a wide range of magnetoresistive magnetometers. This is a tunneling magnetoresistive magnetometer. So what it relies upon is you have two magnetic films, and then you have an insulating layer between. These magnetic films are electrically conductive. So when there is no magnetic field present, because of the spin properties of the carriers and of this insulating layer, no current can come and go across it. When you have an external field, these two planes align. And based on the spin of your carriers, so it's using a quantum mechanical property, your electrons, you can have current. And the resistance is greater than the resistance, is less than the resistance here. And so what you see is as you apply a magnetic field, these are kind of, I would say, arcane units of osterts. That's not relevant for our purpose. What's relevant is that as you have a magnetic field, you get a voltage out from this sandwich of materials. And so now let's look at the specs. Super low power, 1/10 of a milliwatt. Bandwidth, now we're up at a megahertz. The noise floor, not as good. Sensitivity, not as good. Now we're at nanotesla, 10 to the minus 9. So 1,000,000 times worse than the other one. But what's the advantage? The advantage is this goes all the way down to DC, whereas the other one relies upon an AC magnetic field to give you a voltage. And the power is a factor of 10 less. So this just gives you a sense of the trade space. So both of these were classical, even though this relied upon a quantum mechanical effect, didn't involve quantization. We're going to be describing this, but here you get a sense of real world systems. So now we're back up to $7,000 in cost. I like to include that as a metric, important metric. Our powers are a lot higher. Our bandwidths are lower. But now we have sensitivities that are still comparable. Some of them can measure the direction of a magnetic field. Some of them, can't. So this brings up a question, which hopefully I'll answer. Why would you be interested in this product when you have the other ones? And there's a couple of reasons. I'll describe them here briefly. It's the fact that this sensor, its response also depends on temperature. And if you apply a really high magnetic field, it saturates. And once it saturates, this calibration curve, you have to redo it. So this is a nice tool, but it's not a tool that's robust to the environment, nor is it a tool you can rely on for an accurate, precise measurement without having some way to calibrate it in the field, which kind of defeats the purpose, because then you would just use that magnetometer. So magnetic phenomena. And if I'm going too fast, please ask questions. So this is a nice plot I took from this paper where you have, here's the magnetic field sensitivity you required, and here's the strengths of the phenomena, and then here's the frequency of the magnetic perturbation or phenomena. So for geomagnetic phenomena, you can use conventional sensors. You don't have to be super sensitive. But say you want to get into phenomena that involves the human body, which is magnetocardiography, the heart, or magnetoencephalography, the brain. Now you have to be very sensitive. And the most sensitive atomic magnetometers and squids, which I haven't described yet, but will, are capable of that. So this first measurement, this is kind of cool, I thought. It was in 1985, the first time a measurement of a single neuron was published. And I guess I should explain why in the world, or how in the world are we using magnetic sensors to measure the activity of neurons? So neurons, right, are those filaments in the brain that conduct signals, and they conduct it through an electrical current. So if we go back to that first slide, whenever we have an electrical current, we have that magnetic field being generated. And so by having an array of magnetometers around a brain or around some animal, like a worm, you can measure that electrical current through the magnetic field it creates. The plot on the left is one of my favorite plots in the world I've ever seen. So this one slide goes over a few things of interest in geomagnetic phenomena. So here we have the magnetic field strength on the left, and then here's frequency, and it goes from 10 million years to fractions of a second. That's the period, and the frequency is the inverse of that. So, we can start on the scale that we're more familiar with, like a month or a day. And that's the Earth's magnetic field we typically talk about. And so that's on the order of 10 microtesla. Now you go to shorter time periods, and this is just showing you the variations. When you have lightning, well, what's lightning? Lightning's a huge electric current going from the sky to the ground. That's going to generate a magnetic field, right? Circulating around it. And so that can give you microtesla or to nanotesla magnetic fields. And that's not just locally, but above the Earth, about 100 kilometers up, is part of the atmosphere called the ionosphere. It's called the ionosphere because you have the electrons are disassociated from some of the atoms up there. So it's a conductor. And then you have the surface of the Earth, which is mostly water, which is a good conductor. So that creates like a pipe tube where the magnetic disturbances created by lightning can resonate around, like sound through a pipe organ. And those are called Schumann resonances. And so they're at about 8 hertz. And you could even see that. And then you go to higher frequency, you see the ubiquitous 60 hertz, 120 hertz. And then you start seeing radio at higher frequencies. So now we're getting a sense of, well, what kind of sensitivity do you need to measure phenomena of interest? And what's the environment you want to measure it in? Going off of some of those questions, if we want to measure femtotesla to picotesla from a brain, but there's this huge Earth's magnetic field, and oh, by the way, there's all these variations from storms that are orders of magnitude larger. That sets up the challenge. What is a magnetic field made out of? That's a very good question. A magnetic field is a concept to describe electromagnetic phenomena. So just like you have an electric field and we have the electromagnetic field, fundamentally what they are photons, just really long wavelength photons. So this is a challenge of what we do in physics is we have models which describe the world, but can you say that the world is tautologous with our models? Well, not necessarily. At least I wouldn't say so. So I wouldn't offer to say what a magnetic field is. I would say the way we model it is in terms of this thing called a photon, though that's typically not needed for a lot of descriptions of magnetic fields. You just talk about a wire and you've got this influence that comes out and it generates forces on objects. And we all have that everyday experience with a refrigerator door magnet. But I would say the field, it's fun. It's a good question. It's an interesting. No, that's right. So electrons are sources of charge. They're their charge. And that's a source of a field, but it's not the field itself. So if photons make up light, why can't we see EM fields? You can see EM fields, visible light, you can see. Our eyes are only sensitive over a narrow range. And you know how you saw that laser just now? That was a 780 nanometer laser. That's actually just outside of your visible range. You could see that because you have a silicon, sorry to point, but your camera is a silicon CCD. It can see wavelengths of light we can't see with our own eyes. I'll give some practical applications why I would use one versus the other. Here's a really easy one. But if you've ever gone to the airport or a shopping center and you've seen that light above a parking spot, red or green, whether there's a car there, that uses a magnetometer. Do you need a quantum magnetometer to sense a car being over a parking spot? No. Would you spend the kind of money? So I showed you, I'll go back to the slide. So this is the fanciest magneto-resistive magnetometer, and it costs $1,000. The lowest end that you would use for that parking space application costs $5. You know, on your phone, you have a magnetometer. It doesn't need to be very precise to be used as a compass, and it doesn't need to maintain calibration. And what are the likelihoods that your average person with a cell phone is going to go near a 1 Tesla magnetic field? Very low. If they were to, it would ruin the magnetometer. But how many people even use it that much? Not too many, because you have GPS, which we'll talk about next week. I hope that's helpful. And I love these questions. Magnetoencephalography. So what you see here, this gives you a scale of the signals that are seen. 200 femtotesla. Femtotesla is 10 to the minus 15. So this is like, you know, a tenth of a picotesla. And, oh yeah, here I give it a sense of the amplitude and the bandwidth. So these, it's interesting, the frequencies that go on with phenomena in our brains. Pretty low frequency. It's mostly around 100, less than 100 hertz. And with magnetoencephalography, you can characterize someone's processing of speech, of vision, decision-making. You can see the presence of disease or a deficit of dementia, TBI, traumatic brain injury. Although MEG is not really used for that so much because MEG systems are so rare. And that's because they rely on squids, which I'll be describing. And there's some emerging technologies, and some people are even trying magnetoresistive classical ideas for doing MEG. Because here's a picture of an MEG system. So you've got this massive shielded room, and you've got this dome that goes on the head. So there's this dynamic in the medical world about there needs to be evidence before insurance will reimburse for a procedure. But before insurance will reimburse for that procedure, before there's enough evidence, people need to be using that procedure, right? So there's a kind of a chicken and the egg problem. And you see that with a lot of high-end diagnostics and therapeutics. MEG is still kind of suffering that. There was hope in the 90s that it would be more ubiquitous because of what it could do for people with epilepsy and other challenges. And maybe that'll change. But in the current implementation, it hasn't. I'm not sure if there's an MEG system in the area. I remember I was trying to find someone. So this is at the level of research. So this is just from this year of using atomic magnetometers, which would lower the cost and improve the signal for MEG imaging. I'm not sure if they did this on a real patient or not. There are many advantages since it's not cryogenic, squids are, and the sensors, you can bring them closer to the scalp. I actually saw a posting looking for a postdoc to work at NIH on building one of these systems for MEG. So that was kind of exciting to see that the system's being built locally. This data is from Sandia in California. So all of that buildup, possibly I should have started with this earlier, but I wanted to keep the quantum magnetometers together. So here's a squid, a superconducting quantum interference device. So what you have are two pieces of superconductor, one here and one here. And you introduce a break in the superconductor. It's called a Josephson junction, and you have that. And the way superconductivity works is your normal electrons, they just go about in materials. But when a material becomes a superconductor, so if you cool lead, mercury, niobium, I believe aluminum as well, below 10 degrees Kelvin, so about minus 290 degrees Celsius. I think it's minus 560 something Fahrenheit. They become superconductors. What does that mean? They conduct electricity with no resistance. And the way they do that is the electrons pair up to form something called a Cooper pair. And they flow through the crystal with no resistance. When you introduce a break, like a Josephson junction, if it's thin enough, that break, the electrons can tunnel through it. We haven't described what tunneling is, but essentially, it kind of like walks through a wall because there's a certain probability. If you look through the wave function definition, the wave function has a certain probability on the other side. And so then it just goes over to the other side. It appears at the other side. That's tunneling. And by that, there's a communication of the phase of the superconducting state across there. So see, it's an interference device. And we're coming to the concept of phase that has to do with waves. And here's like a more accurate or device level image of a squid. So there's the squid itself, and it's connected to this big pickup loop to for the magnetic field to go through. So it has a larger area to measure. And as the magnetic flux goes through there, you see a sinusoid. The period of it as a function of magnetic flux or B field is 1 flux quantum, which is about 2 times 10 to the minus 15 Tesla per meter squared. So the bigger your area, you would divide this by the area to see the field you're sensitive to. The bigger your area, the smaller fields you're sensitive to. And so what are we seeing here? We're seeing quantization, and we're seeing coherence. So this was first developed in the late 60s. So quantum sensing has been around for a long time. But it's getting more exciting recently. So I have a question. So based off this definition of a flux quanta, and based off the area of the pickup loop, what's the magnetic field associated with that flux quanta? And I will give 1 minute for you to do the math. So, what's our area? 64 times 10 to the minus 6 meters squared, because a millimeter is 10 to the minus 3 meters. It's millimeters squared, so that's 10 to the minus 6. 8 times 8, 64. Phi naught, we defined as, and this is exciting, here's h bar again. So the flux quanta is defined in terms of pi, the irrational number, Planck's constant, and the charge of the electron, all fundamental numbers. That's why our definition of the volt is actually defined in terms of using a Josephson junction, because that response is based off fundamental constants. So that's 2 times 10 to the minus 15 Tesla times meter squared. So a thing I often use, which I was taught, is dimensional analysis. If we go back to the question, we're given a flux quantum, we're given an area from geometry, and we're asked for magnetic field. Well, how do we get a magnetic field out of this? We've got to divide by area, right? That's the only way the units work. So sometimes you can just figure out an answer to a problem by looking at the units. So that means we need to divide the flux quanta by the area. And that's why if we have a bigger area, we've got a smaller magnetic field. So that's 3 times 10 to the minus 11 Tesla, or 30 picoteslas, where a picotesla is 10 to the minus 12, or 1,000th of a billionth. So that shows why it's a really good sensor, because if you go back, that's for a whole flux quanta. But if you sit here on that slope, you can measure a fraction of that. And you're just measuring it going up and down. The changes up and down on that slope. You don't have to measure a whole flux quantum to make a measurement with the squid. You just sit right here. You look at the changes of the voltage. So let's see. Yes, weaker or smaller. By bigger area means that it's a smaller field per flux quantum. So atomic vapor magnetometers. Some of you may have remembered I was alluding to that we would talk about MRI in this section. I decided not to. But the reason why I wanted to is because the physics of MRI systems is very close, is the same physics that we're going to talk about with atomic vapor magnetometers and with the solid state artificial atom magnetometers. So what is our system to begin with? Let's start with the physics package. We have a vapor of an alkali metal. Alkali metals are interesting because the state of the outside electron is kind of simple. We have heaters because so our vapor is in a glass cell and we want it to be a vapor, not just a pool of stuff at the bottom, but we need all the atoms making like a gas. We have a laser source, some optics to collimate the light or manipulate it, the polarization specifically. And then we have a detector. We also have coils where we might apply a radio frequency field. So how does it work? The light we send through the vapor actually polarizes the atomic spins by, and we'll discuss it in the next slide, it polarizes it by putting them in the same spin state. So that's optical pumping. When you're in an MRI, there's a giant magnetic field source you're sitting in, right? MRIs are Teslas of magnetic field you sit in. What that's doing is all of the hydrogen atoms in your body, some fraction of them are being aligned along the axis of that magnetic field. So that's a form of magnetic pumping. And that alignment is necessary in order to do the pulse sequences. So whereas in this system, we're making an alignment with light. There's some interaction with the magnetic field which perturbs that alignment. That perturbation is measured by this detector because it changes how much light is received by the detector. So we talked about very briefly. So if you circularly polarize a 795 nanometer laser, it state preps the atoms by pumping the atoms into a specific quantum state. So if you remember with the Balmer series from last week, the electrons had discrete energy levels around the hydrogen atom. And when you excited the electrons in the hydrogen atom, like our neon tube, they emitted light at a specific frequency. Here we're doing the opposite. We're shining light of a specific frequency tuned to the atomic transition to make that electron excited from an orbital angular momentum state of 0 to 1. So we talked about the spin of the electron being 1/2, and that as you excite the electron in an atom, it has different orbital angular momentum. That orbital angular momentum interacts with the spin of the nucleus. And that's the interaction we're going to take advantage of, which you'll see now. So we have our system and we're pumping it with circularly polarized light. This is the spin quantum numbers for that interaction between the electron and the nucleus. And every time a circularly polarized photon hits an electron, it has to give it angular momentum. So the thing is, the numbers only go to m equals 2. That's the highest state it can have. So what happens is, as you shine light on the vapor cell, and this takes time, you push all of your atoms, all the electrons of those atoms into this state. It takes about 20 milliseconds. And then that cell becomes transparent. The light just goes through it because the light can't interact with the atoms anymore. But then you have some magnetic field, ambient magnetic field. What it does is it interacts with these electrons and it changes their state. So then the light can interact again. So then the vapor is not transparent anymore. So the changes in the transparency of the vapor is what you're measuring in order to measure magnetic field changes. So here, there's no magnetic field change, and the light just goes through the vapor. You apply a magnetic field, and it absorbs, and you get less light. Here's our system: the circularly polarized light, the vapor, the circularly polarized light that gets through to the detector. The detector, I don't know why I drew an amplifier in there, not necessary to explain. And that's what you see. So this is one of the most basic, and I thought this is where we should begin. The most basic atomic vapor magnetometers. They can get far more sophisticated. But what we can see already is look at the time scale of this polarization. It's 20 milliseconds. So that's on the order of, a few hundredths of a second, right? So that's why the bandwidth, if you remember, it's like 100 hertz. It's because of that. So the fundamental physics limits the frequencies you can measure. But if what you care about is MEG, does it matter? No. Because all we care about is stuff around 100 hertz. So there's a perfect application for this very sensitive magnetometer. So how long have these magnetometers been around, you may ask? Since the 70s. What's the difference between now and then? It's our ability to control the laser light. It's our ability to detect laser light. And it's what we've learned about how we need to manufacture and control these vapor cells. That's what's changed. But the physics has been known for 40 years. It's actually a really interesting story. So this is our last quantum magnetometer. So what do you see here? You have green laser light, but you have this red glowing thing in there. That's a piece of diamond. Why does the diamond have that color? So why do most things have their color? You see yellow, red, blue, orange. This has its color because of the light it reflects, right? Because I have white lights in the room, and this reflects certain colors. And that goes to your camera. Your camera accurately processes the colors, and your monitor does, and you see the right colors. With diamonds and other wide bandgap materials, they don't get their color, for the most part, from absorbing or from what they reflect. They get their color because of the luminescence, because white light's hitting it, and that's exciting these point defects. What's a point defect? What it is diamonds made out of carbon, right? And it's this regular array of carbon. If you take out one of those carbons and you put a nitrogen right by it, you create a nitrogen vacancy center. And when you shine green light on it, it'll emit red light. And that's what you see here in this diagram. So wide band gap means that when you take a bunch of atoms together and you make a crystal, the inner shell electrons form something called the valence band. And the outer shell electrons form something called the conduction band, and you get a gap that opens up. If that gap is really large, like more than a couple of electron volts, the material is transparent to visible light. It's clear. You put defects in it, then you get these states that can be optically excited and fluoresce. So here we're pumping it. I know this is red, this should be green, and this should be red. So you put in green light and you get red light out, and you have a beautiful picture of it. How they did that, I have no idea, but that's one of the prettiest pictures I've seen to show that fluorescence. And so here's examples of diamonds with defects that have these beautiful colors. This is one of my other favorite plots. So what mobility is how easy it is for electrons to move in a material. So how good the crystal quality is. The band gap we just discussed. The circles are the thermal conductivity of the materials, the area. So how well they conduct heat. Really, there's only 3 materials that you'd be interested in. Silicon carbide, gallium nitride, and diamond. And diamond is the best of all of them. And that's why this type of work started out in diamond. So I mentioned the diamond nitrogen vacancy. There's 2 leading defects for this field. And I'd say the real leader is the diamond nitrogen vacancy. It's been studied since 1997. So that's like 23 years. It's been known about for decades before that, but I'll show you the paper where they showed this phenomena first. It's a beautiful paper. You can make these defects by putting electrons on them, shooting nitrogen ions at it, and actually with femtosecond laser pulses, really fast laser pulses. And this is another system. This is actually a system I study. I've been studying for a few years. It's a silicon vacancy in silicon carbide. There's reasons why this is more interesting, but it just hasn't been studied as much. The basic physics of this was understood maybe 10 years ago. The basic physics of this defect was understood maybe 5 or 6 years ago. Not that different, I guess. So how does this work? So I mentioned you excite it with light, and then it emits light. But you spin polarize this thing. How are we spin polarizing it? Well, diamond has over 500 color centers or optically active defects. Maybe 2 or 3 of them are interesting. And the reason is this thing called an intersystem crossing. Because you pump it up here, and depending on its spin, it'll decay there and change it to this other spin when it comes down here. So that intersystem crossing spin polarizes your artificial atoms for you. The crystal does it for you. That's really cool. By optically pumping, the crystal structure spin polarizes these defects. And there's a T2 time, there's a T1 with this spin polarization associated with it. So we talked about that fluorescence for diamond. You shine green light at 532 nanometers, and you get all of this red light out. What ZPL is the zero phonon line. So this is at room temperature. If you were to cool this crystal to cryogenic temperatures, all of your light would be there. It's the interaction with the crystal lattice which broadens out to higher wavelength or lower energy the light from that defect. And here's a basic experimental setup where you have your pump laser, 532, you have a special mirror that reflects green light but lets red light pass. It's called a dichroic, 2-color. So here's that beautiful article. They irradiated this diamond with nitrogen. They dialed down the dose until they could see these little fluorescing spots. And they were able to do optically detected magnetic resonance on it. So here's that red emission we talked about. And at 2.8 gigahertz, it splits the spin states. And so here's that intersystem crossing I was mentioning. It takes the spin equals 1 stuff and then pushes them to spin equals 0. So that's how you get optical spin polarization with the system. Now that 2.87 gigahertz, which would be here, when you apply a magnetic field, it gets split. So this is a change in fluorescence with applying a magnetic field of a certain, with applying a radio frequency field and a magnetic field. So you use that radio frequency field to interrogate, and that's how you can measure B fields with it, magnetic fields. I call them B fields. I'm not the only one. And what's cool is in 2017, people showed you could look at the neuron of a worm using this. It's an okay article. It was okay, I say this because I've read this article probably a dozen times, and I thought, wow, look at the great response they got from the worm, right? And it was fitting their modeling, how it should look. But then I finally noticed this weekend when I was preparing these slides, each of these plots, they averaged 1,500 signals to get it. So that's a little bit iffy to me. But I want to stop in case there are questions.